Can start. Yeah, thank you.
Thank you all for inviting me to this seminar. Well, I started to think that this seminar was better to do it, at least to introduce the relational formalism. That's something that I will extensively use throughout my PhD. So basically, I want to introduce this topic, which is not very popular. At least just few physicists do research about this. So this is not straightforwardly connected to what I did in the previous seminar, but I thought that this is very important to know, at least some basics. So what I will do is just to introduce the concepts behind relational formalism in classical mechanics. So by classical mechanics, I mean just from Hamiltonian formulation. And I just give an example, a very simple example, which is one-dimensional harmonic oscillator, at least just to understand how it works, at least the concept behind, and also I'd say graphically speaking what it means. And I tried to apply it at least to the field theory, but this will be just an introduction because it's quite a broad, there is a lot of theory. So I think I cannot cover entirely this today. So what I plan to do is to divide all I want to say in two parts, namely today I'm going to discuss about this, and the next seminar that I will, I think next month or something like that, when I have time, to continue and to apply this concept to general relativity, or at least the Hamiltonian canonical formulation. So this is the same slide I showed the last time. That is, we make a difference between partial observable and complete observable, because a partial observable is a phase space function which can be directly measured by some device, but it's not predictable in the sense that since it is not gauge invariant, namely we cannot at least explain its dynamics with respect to some other quantity, namely to some other variables. In order to get what we call complete observable, which instead is again a smooth phase space function, but it is both measurable and predictable. Predictable because it is invariant under any gauge transformation, which in the Hamiltonian formulation can be given just by the constraints that we have. So the point is to relate two partial observable in such a way that we get a complete observable, which is just a physical observable. This is what it means.
Okay, can I ask a question?
Yeah.
Okay, so so it seems like, I mean, from what you told us, you basically use the word predictable to be mean gauge invariant.
Yes.
Or is there any difference other than semantics?
No, well, of course, yes. Predictable means gauge invariant because we have well-defined dynamics, and what we get is gauge invariant. So that's a synonym. Yes,
synonym. It's a synonym. Good.
Yes.
What can you mention something which is not measurable?
Well, yeah, okay. The first thing is that not measurable in, you mean with by some device, or
what do you mean?
I mean that, for example, suppose that well, I guess I'll get to this in the example of the harmonic oscillator. But as an introduction, I just say that, for example, take the time t and the position q of a particle. If, of course, we can measure both time and the position, but without relating them, namely without relating the position at a time q, both t and q are not predictable because, of course, it's just a kind of measurement. Okay, so only if we compare them, namely we have a function of 2, we get, yeah, you can say a dynamics or an evolution, or just a relation between them. That's what it means, because, well,
but then it sounds like it's a little bit like the predictable, that you know how the time evolution is.
Well, no, you have to think them separately. Like we have a clock and we have a ruler, but if we don't compare them, of course, we cannot have a relation between the position at a certain time t, but only two different systems.
Okay, so right. So the things we're talking about is time and then phase space.
Well, of course, time can also be treated as a coordinate in the phase space.
Okay, so what's really a difference between it?
Between, you know, of course, from the phase space,
of course, you can have covariant phase space, but time is also part of it. Yeah. But then I think, so, I mean, I can think of many different things that measurable means. I can think of measurable in quantum mechanics, whether on the Heisenberg uncertainty relations.
Yeah, in fact, this quite,
but
broke this. Yeah.
We're talking about classical theory.
Yeah, exactly, classical and field theory, but in the beginning without quantum mechanics.
So then measurable presumably has nothing to do with
no, the fact that for example, one operator is self-adjoint and so on and so on. Not in that sense. Yeah, that's why this is classical theory in the beginning, just to introduce it.
Okay.
So we have, trajectory. We have everything that we can measure in classical theory. There's no problem of position and time uncertainties, for example. And so, yeah, for example, two partial observable can be time and the position, or can also be, for example, the position and the momentum and time, and so on and so on. We can make almost infinite kinds of partial observable. The only thing that matters is how to relate them in such a way that we have a well-defined relation between the observables. That's basically what it means. In fact, the first thing that we have is just, smooth symplectic manifold with the phase space as the cotangent bundle, which is even dimensional, and just a symplectic structure. And so we, for example, we can pick local charts, and so that Q and P are local coordinates of gamma. And since we have a well-defined symplectic structure, also the Poisson bracket is well-defined. And we said this Q and P to be a conjugate pair. Of course, in Hamiltonian formulation, we have also a general Hamiltonian function, which is just a smooth phase space function. And so that we can associate to this Hamiltonian vector field, which can be derived just from the fact that df equals plus or minus, depends on the convention that we want to use, the contraction of the symplectic form by the Hamiltonian vector field. That's something we know. And we have also some vanishing constraints for I that can run from 0 up to 2n, for example, which define submanifolds in the phase space. Namely, they reduce the degrees of freedom, and they are first. I remind you that first class means that if we take the Poisson bracket between this constraint set, then the resulting will be linear combination where f can be either just constants, and so are called structure constants, or structure functions if they function on the phase space. Basically, this statement is, I mean, this feature property is very important because this is in analogy with the involutivity of a distribution, because if we have a tangent bundle and a distribution just as a submanifold described by some vector field, then the fact that the Lie bracket, just the commutator between the vector field, takes the same form, means that we basically never get out of that surface. Yeah, in fact, this is displayed in this picture where, just to simplify the discussion, suppose that this phase space is this cube, entire cube, M, and this M bar is a submanifold described by the constraints. Yeah. Usually they're called hypersurface, constraint hypersurface, even though the codimension may not be one. So constraint hypersurface just stand for constraint submanifold. And if we have a point here on this submanifold, we denote this line, this curve here, with just a little m in bracket, which is the gauge orbit through this point. Okay, so this is given just by the flow on the phase space restricted to this submanifold along the Hamiltonian vector field associated to the constraints. So the first class property means that if we stand here and we calculate the flow, then we stay on this hypersurface. And with this M with the hat, this is called the reduced phase space. And basically, just roughly speaking, this is curve here represents all different physical points, namely physical observables in the phase space. Because any point here, for example, take this point here, and we know that the gauge orbit is this, then all these points here are physically equivalent. So all these points in this M bar are physically different. That's what it means. So now just call for simplicity sigma a random point in the phase space. Now the flow generated by the constraint, of course, induces a flow of the function, because any function f, which I remind you, this is a partial observable, namely just a smooth phase space function, takes a point in the phase space and maps it to a so-called target space, which generally is Rn, or just some submanifold of Rn. And so this flow on the phase space induces a flow also in the target space. And so the flow associated to this f is defined as the exponential map of t, which is a parameter, not exactly a proper physical time, just a parameter. And with L here, we have the Lie derivative along this Hamiltonian vector field associated to the constraint acting on the function f. And it's very simple to prove that this corresponds to this power series, where the subscript k just stands for this, namely, these are called the iterated Poisson brackets. So we have infinite terms like this. All is right? Okay, so again, we consider two partial observable, so say T and F. So a complete observable is that we denote by this capital F involving these two partial observable at the point sigma.
So again, what would be example of two smooth functions which are not partial observables?
Which are not partial observables.
Right. So what does partial observable mean?
Partial observable can be as defined as any kind of smooth phase space function. So almost everything in the phase space.
Right. So it is just two smooth functions.
Yes.
Okay.
Yes.
So something not necessarily gauge invariant, is that the thing, or do I get it wrong?
That is not a thing. That's what he started with. Are you just coming now,
Yes.
Andra?
Yeah, I came a little late. Sorry if that has been discussed.
He explained that's called a complete observable.
Sorry.
But it
Yes.
seems like a partial observable is an empty word. I don't see any meaning to it. Any C infinity function is a partial observable.
Well, I guess that this the name itself created by Carlo Rovelli is just to distinguish between two kinds of observable. Partial means just
That's
partial.
basically anything. That's anything.
Yeah, it's just a different name to call a smooth phase space function. Yes, but it's called, I guess it was called partial because it's not exactly complete. Namely, it's just a part.
It seems like it's just renaming what everybody else agrees on. Partial observable, that's just a smooth function, and complete observable, that's a gauge invariant function.
Yes, that's the same thing. Yes. So this means basically that we calculate the flow of the first partial observable and ask where, at least for which t, and of course for t, I don't mean just one single t, but it can be many, also infinite, if, for example, this flow is periodic, for example, but where and for which t this takes a parameter value tau. Okay, so if we can basically invert this relation for t and solve for t and insert this t in here in this other flow, then all this f is can be proved simply. It's not very complicated. That is a complete observable, that the flow generated by the constraints, which are based on gauge transformation, doesn't affect this observable here, this function. So the algorithm is simple. That is, we compute this flow at a certain point sigma in the phase space, and then we set it to be tau for some parameter tau, exactly when this takes a value tau, which of course has also a deep meaning, because basically it means on this gauge orbit, if I take a measurement and I measure tau, okay, so we have exactly a number, for example, then if it is analytically possible to solve for t, then when you compute this other flow of the other partial observable at the same point sigma, and we substitute the t obtained here into here, then we get, I want to stress, not just a single valid function, but more often we get multi-valid functions, and I explain you why. We can get many functions. So now this example, just simple, namely just for one-dimensional harmonic oscillator, we have the phase space is isomorphic to R2, so these are global coordinates. The Lagrangian is given by this with K, the spring constant. And also the Hamiltonian is something that we know, so nothing more to say. And the Hamiltonian is constant, namely it just set an energy level that the harmonic oscillator has. And since there is no friction term, this is constant. Therefore, the Hamiltonian can be treated as a constraint of the system, namely it doesn't change. And here we treat Q and P as partial observable. And by this, I mean just that you may ask, okay, but Q and P are coordinates, not functions. But this is just what I mean. What I mean is just take the Q as the first partial observable, which is the projection of this point onto the first factor, and P as the projection of this point onto the second factor. So that's basically what it means. Is it clear?
Sure.
Okay.
But
So
I guess this f function is not completely clear. But okay.
yeah, but I guess you understand now. So now this with H, the constraint is basically a complete observable, and we'll prove. So the first thing in the say algorithm is to calculate the flow of this. I just got rid of sigma here, the point, because I just saying that the function applied at the point sigma is Q. So basically our first partial observable, let's say T here, is basically the projection of this sigma to the first factor, namely Q. That's the point of the function. So the flow is given by this, okay, we have infinite terms, but we can rearrange them, namely, for example, take only these two terms with the red underlines, involving namely only Q. And if we set just these two constants here, just for simplicity, this is well known. Well, these two are the first two terms of the cosine here. And the other with the blue line are just the first two terms of this sine. And this is an exact solution. This is not approximation. So doing the same with the flow of P, we get this other one. And of course, you see from this that I show here, these Q and P are just constants, namely just a point from where we start. And if we treat them as what they are, this flow is just Q of T, namely just the solution of the Euler-Lagrangian equation, with initial position this. And the P of T, the flow of P is just P of T. So basically this one is just the time derivative of Q and multiplied by M. So from this, we see that these two flows coincide with, we started from the Hamiltonian formulation, this coincides with just the Lagrangian formulation. So far it's good. Now, just to make a picture, say that, for example, the mass is 1, the spring constant is 4, and the initial position is -1, and the initial momentum is 0. So basically it starts from -1 and goes rightward till the point +1 position, and so on and so on. So we know the dynamics of this system. So Q and P are given by these two. And the picture is that we have a curve describing the phase space where we start from T equals 0, where Q takes the value -1 and P 0. This is the direction of the evolution, the system. And yeah, this is periodic. That's not something to stress more. But what is important here that we draw this curve here by this parametric system Q of t and P of t. This is not given by, as you see from here, just P with respect to Q. And now this is the point, the core of the relational formalism. Because how can we relate P and Q directly without saying Q at the time t takes a certain value and P at the time, a certain time t takes another value. But we want to have P with respect to Q. And of course, in this case, simple case is just to invert the relation and substitute here. So nothing special. I just want to say that, okay, this flow here, the first one and the second one can be also written in these two forms, okay? So that we can exactly, when we set this first flow to be tau, and of course tau as a physical dimension as Q, namely, yeah, the dimension of the position of the harmonic oscillator, then we can invert this relation. And what we get is omega t0 two solutions, periodic of course, and these two are different. Okay, this is just a matter of calculation, nothing special. When we now insert these two solutions into, this one, the second one, the second flow, we get, of course, two solutions here. One with the plus and one with the minus for the two different solutions. And for alpha, Q, and P, yeah, the same constants as before, we get that these two flows at two different time t0 and t1 are plus p0 and minus p0 of tau. So basically, what changed is now that we have the momentum not with respect to time, but with respect to tau, which basically means the position of the harmonic oscillator. In fact, if we want to draw these two, we get the exact curve as before. Namely, we start from this, we are going here with the plus solution, and we glue the minus solution at the edges. And this is a graph, of course, because we have tau and P of tau. And you see why we get two solutions of the functions, these two, not only a single valued form, because we cannot, as a graph, draw a curve with only a single valued function. So it's nothing strange if we have nothing wrong if we get multi-valued functions. And so now this, so as I said, describes just P with respect to tau. So that's exactly the momentum with respect to the position. Namely,
can I ask a quick question? I'm sorry, maybe if you said that in the beginning, then I apologize and please disregard. But,
yeah, don't worry, don't worry.
If so, what does this thing measure? Like I understand what Q and P measure, and what is this complete observable? It seems like I just dressed it with the time evolution. Like it's sort of like a classical analog of.
Yeah, in this case, this is very classical analog. Yes. Of course, it's not just a time evolution. It's just how to relate two functions. So in this case, this is not a time evolution. Namely, it's not evolution in the sense that we how we treat time, but this is analog to the time evolution because it just says, well, when the position tau regarded as a time clock takes the value -1, then the momentum takes the value 0. And when we measure tau 0, it takes the maximum, and so on and so on. So basically what we have is that this P of tau now is a complete observable, because this is a kind of a dynamics predictable.
So can I think of it as, you know, like normal observables, they're in fixed time, right? They are functions on the phase space, as you said.
Yes.
But clearly there's this extra dimension, the time, and
course.
so I really have the 2n plus 1 dimensional space, and this sort of spreads the original observables.
Of course, you can also create the presymplectic space by introducing just the time. And so this, instead of being just an ellipse, will be an helix.
Yeah.
You know, just
right.
Going like this.
Yeah.
And so we're just basically projecting that helix onto a plane.
Right.
But of course, I can also, in fact, I thought also to exhibit the other picture that you have just mentioned.
Okay.
But finally, eventually I decided not, otherwise it would be too long. And
okay.
The basic concept basically like this.
Maybe Andre, I think I get it somehow. I guess if we think of the Hamiltonian as a constraint, then we have a gauge symmetry. I guess that is time.
Yes, exactly.
Evolution, and I guess what Giacomo is getting at with the complete observable is that if you just specify momentum or position, then it's not a gauge invariant, because in the future it would be something else.
Yes.
But what would be a gauge invariant is if we also specify an extra information, and I guess that's the clock tau, or
yes.
If you specify two. So I guess this is the role of this capital F function that you showed before, but maybe you should explain in words what this capital F function you had 2 slides ago.
So I might as that's what I was thinking originally, that it's like smearing it over the gauge orbit or something like that. But
not exactly,
not quite right.
But it's more like that you make a precise statement in a reference to something else.
You mean where?
Yeah, you introduce this F function. Yeah. So how should I read this? There's a tau and a sigma, and so so this alpha TC, that means the evolution of.
Okay,
F.
basically the meaning is this. We have a partial observable, just a phase space function T, and we create, the flow. This is the gauge orbit of this partial observable at the point sigma, namely passing through this point sigma in the phase space. So we have a gauge orbit in this case where this constraint is just one constraint. This is just a line. So just a curve, one-dimensional. So when this takes along this orbit, gauge orbit, a value tau, then exactly at that point, when we evaluate this other flow, exactly in that point, basically this turned out to be gauge invariant. So it's not simple to explain it. It's something that you read more from formulas, but the point is just that we make evolution of two partial observable, which at the beginning are not connected, but when under the same Hamiltonian vector field, which generates basically a gauge orbit, when the first one, and can be, I can also exchange them, it doesn't matter. When the first one takes a certain value tau, exactly at that time, when we measure this second partial observable gives something that I can both measure, but also doesn't matter on the gauge itself. Well, by words, it's not simple to.
Can you maybe, if that's something simple, if suppose I picked not any observable but gauge invariant observable, what would this f give me if I applied it on already gauge invariant observable, right? Like on a constant of motion, if you will.
Yeah.
Here,
You mean if I just choose
some function of h, I guess.
Okay.
Yeah, or
Well,
H itself.
Or H
exactly,
itself, right.
exactly, because from the Poisson bracket between the constraint and well, which is in this case the Hamiltonian, and the function of the Hamiltonian itself vanish. So we get basically what remains is just the first one. Okay, just
Oh yeah. Oh, okay.
it will be just this one. So
Yes.
the function itself. So,
So
it
it's
means
kind of
that
like
it's a constant of motion.
So it's kind of like a projector in a way, then.
Yeah,
like
yeah, yes.
Okay.
Yeah, you can think of that. Yeah, because we can start, as I said, from the presymplectic phase space, and so by presymplectic just introduce time, but not the momentum
I think that's not
associated
called
to t.
presymplectic. That's called contact structure. Contact
Also,
space.
yeah. No, it's called in both ways. Yes. So I just introduced in the configuration space the time without adding its respective momentum. Of course, it's contact by mathematicians and perhaps presymplectic for physicists. But it's the same. Yes, exactly. You can call them whatever you want, but they're the same. Yeah.
I would say presymplectic is a more general notion.
I thought presymplectic is just phase space with not necessarily closed symplectic form, whereas
no, you have a closed symplectic, but it's non-degenerate. Sorry, it's not
okay.
non-degenerate.
Yeah, but that doesn't just have to be a time direction.
Yeah, and contact is something else, right?
Yeah,
Contact is when I have one form dt minus, I don't know, q dp or.
Yeah, a presymplectic, what I've heard is that that you just drop the invertibility of,
Yes.
of
Yeah, it's the true form is still antisymmetric, but is non-degenerate, and in fact there exists.
It's still closed.
Yes, it's still closed, but there is one single Hamiltonian vector field, which when inserted in the presymplectic, in that form, exactly is zero. So omega, that form, this one contracted with x is zero for for some vector field x, which is non-zero.
Yeah, I think you're talking about the RAB vector field.
Well, it's given by basically the same vector field that we have, just the Hamiltonian vector field, but adding the d of dt, namely the new vector associated to the time direction. So if we add just plus d over dt, then it solves omega x equals 0. Okay, so but of course this is just just to show that these are equivalent and this makes sense. But the powerful meaning, the core of this relational formalism is not to have something that we can also have, from just theoretical point of view, but with observations. That's why I made this picture here, because once we get this p of tau, and I just remind you that generally is this. Just suppose, for simplicity, that the mass and k, the spring constant, are given, but we don't know where it starts, basically from the initial positions. So just imagine that someone else prepared this experiment for you, namely just a person displayed the spring up to a certain point that you don't know. So basically you from the beginning don't know the level, the energy of the system. But by measuring, at least by making some measurement, you can get exactly the energy level, and so the evolution, for example, of this momentum with respect to the position. Because, yeah, of course, from theoretical point of view, we have any kind of theory, many constants that we don't know, for example, that has to be fixed by experiments. So this concept mixes the empirically, or at least observation, with the theoretical structure. Because as I said, suppose that we don't have P and Q, the initial positions. So these are just three ellipses that might describe the evolution of the system, namely just the energy level of the harmonic oscillator. So how can you know that only one is correct and the other ones are incorrect? Basically, we can make a measurement. Suppose that we have a ruler, very precise ruler, measuring the position and at the same time measuring the momentum. So from that, we get a point, of course, in this two-dimensional plane, of course. And suppose that we get this point here, namely when tau is 0, we get P equals -2. Okay, so from this we know that this is the ellipse, and so this is the dynamics, yeah, say in quotes, dynamics of P. But of course, for this we have to make two measurements, one for tau and one for P, to fix the two unknowns, which are P and Q. Of course, if we don't know also M and K, we have to make 4 measurements. And so we have to make as many measurements as unknowns of the system. Of course, if M and K are different from 1 and 4 respectively, we have totally different ellipses. For simplicity, I just showed for M1 and K4. But this is the point. This so basically mixes experimental experiments, yeah, and the setup of the theory. That's the core of the of this formulation. So yeah, I just make 3 considerations that this F is indeed a complete observable. That is, it commutes with H. It is, in fact, this is equivalent to this other one, with where H is the Hamiltonian. So this, since this is proportional to Hamiltonian and this tau, which is a parameter, of course, this commutes with H. And also, other thing that we did was, instead of having 2 different dynamics, one for T with respect to T and P with respect to T, we have here P with respect to Q, basically. Namely, we can predict the momentum just by measuring the position Q and say that that measurement gives the value tau. And the last, which is much more ironical, of course, is just, of course, we know that the universe is not as simple as an harmonic oscillator, so it's not silly, pointless like studying harmonic oscillators. So we have also to extend this formulation for field theories, which describe the word that we know. So if we want to, yeah, to carry over the relation formally, yeah, carry over the field theories, we have also an additional structure, which is the, say, just for the dimensional manifold, because in the next seminar I'll just focus on general relativity, but of course it can be extended to any dimension. So we have this manifold with basically just denoting points X. And what changes? Well, we get much more complicated structures because we have not only say k constraints, but we have k to the infinity because each constraint is different at each x. So we have infinitely many constraints, each for any x in the manifold. Also, what difference is that we don't have just a fixed phase space, but also the phase space depends on the point, because for say fix a point, and then exactly at that point we have fields which give rise to this phase space. And so since the points are infinite, we have 2n to infinity phase spaces. And this is not something very nice to see, because we have to treat with infinitely many constants and phase spaces. This complicates a lot the framework. So of course we have also just general fields on M. They can be scalar field, vector fields, spinors, and so on, whatever you want, basically. And this can be thought to be something not so important, but the fact is that we can integrate over the manifold M, namely we can smear the fields, which can be just coordinates for the phase space. And why is this important to smear the fields? Because, well, suppose that we have k constraints, okay? And of course, we have k constraint per each point. Now, if we integrate over the manifold with some test functions, which are also called just smeared functions, which are independent from the phase space. And this is also very important. And I explain just a little bit why. Just depend on the point of the manifold. Now, this is done for several reasons. The first reason is that it may happen that at some point these constraints are singular. So if we smear, we might remove the singularities and have well-defined quantities. The second reason is that the total Hamiltonian, which is a constraint in ADM formalism, is exactly a smeared constraint, where the test functions are the Lagrangian multipliers, namely just the shift function, the shift vector and the lapse function. And the CI are just the four constraints that we know, the scalar constraint and the diffeomorphism constraint. And another reason is that now this can be thought also as a constraint, namely if this smeared constraint also induces constraints, also induces flows for the partial observables. But now they don't depend on the point X, just depend on the test functions lambda. And yeah, I'll briefly get to this. So suppose that we have as many partial observables as constraints. And this is done for several reasons. But I'm not going in detail to explain this, otherwise it would take too long. And suppose that we have another partial observable, just a general field psi of X. In this case, sorry about that, this is supposed to be psi instead of F. So now in this case, the complete observable is given by this. So basically the structure is the same, the concept is the same, but instead of having function on the phase space, we have fields on the manifold applied to the point sigma of the phase space. Because, in the phase space, for example, I can take as a coordinate just, for example, a scalar field. And we have also the momentum. its momentum, which is a coordinate in the phase space. And yeah, that field is exactly, can say, yeah, just a function in the phase space. So basically, that's what it means. We calculate this field in the point sigma in the phase space. And yeah, we set to be tau dependent on J, of course, because for each T we have different tau. Also, this is not anymore a parameter, but a field, depending on X, of course. But the flow, or what difference that now we have this mirrored constraint instead of just the single constraint depending on the point. And we no longer have T, because, you know, that T can be reabsorbed into these lambdas. When we evaluate the carry out Poisson brackets, that can be reabsorbed in this general lambda, not fixed lambda. So we just get rid of this T. We can just set T to be 1. So yeah, I guess I don't know if I'm going over time. I'll try to be yeah, very not explaining in detail, because otherwise it would take too long time. But basically, okay, what we have here is that, again, we have to calculate this flow and set it to be equal to tau. But here, instead of solving for T, we have to solve for the lambdas. Okay, and then if we can solve for the lambdas, we basically substitute the lambda in here, and what we get exactly a function which is gauge invariant. But most of the times, yeah, because of many reasons, because we have many constraints, because this is a field theory, it's not possible, analytically possible, to solve for the lambdas. So what we think is that, suppose that the first term in the Poisson bracket involving this flow, which is this, okay, is given by this K by K matrix. And suppose this is indeed the case, for example, in general relativity, so this is a good assumption, this is invertible, namely that it satisfies this equation. I mean, that A minus 1 is just the integral kernel satisfying this relation. If this is indeed the case, then if we can set the new constraint, and this constraint we can see that since involved the Cj, also this C describe the same phase space submanifold, so they also vanish. And now, what is the structure? Well, they're weakly abelian in the sense that the linear part of this Poisson bracket involving, just as I said before, F multiplied by C, which is the constraint, well, that term weakly vanishes, but weakly vanishes not because of the constraint C, because any component of the structure function weakly vanish. So what it's left here is just that this Poisson bracket is quadratic in the constraint, and this G do not weakly vanish. So this is again a first-class constraint in the sense that this preserves the submanifolds. We never get out of that. So far so good. At least this algebra is good. So this is not strictly abelian because we have a quadratic term, but at least the linear term weakly vanishes. By doing this now, we just follow the algorithm and say, okay, now I calculate the flow of Ti with this mirrored constraint. Okay, of course, this is given by this. And what it turns out, and it's simple, that on the constraint hypersurface, this is linear. now. Namely, this flow of T along the Hamiltonian vector field associated to this new constraint evolves along this coordinate line, T. That's why this T can be treated as clock observables. And so this simplifies a lot, this flow on the constraint hypersurface. So the next step is, okay, as said, we just set this to be tau I. And now this is simply, we can simply invert this. And so this lambda is weakly equal to this. Sorry, this line should be also be extended up to this. So that's why we introduced this new constraint, because it simplifies a lot. Now we calculate the flow of the other partial observable, and this flow is now much more complicated because we have infinite terms involving infinite integrals in the power series. So this is just the first term, just the linear, say, term in the Poisson bracket. So how can we deal with this? At least how can we cope with the fact that we don't know basically how to simplify all these terms? Well, we know that by the property of the Poisson bracket, we can this can be decomposed into parts. Namely, the first part, this lambda gets out here, and we are left with psi and c tilde, Poisson bracket, and the other one is just psi, Poisson bracket between psi and lambda with c tilde outside. Okay, and this happens for all the other terms. So now, since the term with the c tilde outside weakly vanishes, we can just say, okay, this on the constant hypersurface is given by all this lambda outside, and the other terms with c tilde outside are just cancelled. So now substitute exactly what you found, that is lambda given by this, into this, and we get this one. Okay, we just substitute this lambda with this. And now the fact is that we have to treat this complete observable with infinitely many integrals. But the point is not that we are not concerned about the integrals. We're concerned the fact that about the fact that we have to calculate all these Poisson brackets between psi at the point x with all the constraints at different points. So we have infinite constraints evaluated at different points. So if there is something that we can do to cope with this, then of course it will be much better. Generally, it's not possible to simplify this, but if we make an assumption, another assumption, namely that this matrix, and this is the last slide, so I don't want to bother you anymore. Namely, this Poisson bracket, the linear term, is ultra local, namely, it's just proportional to the Dirac delta. It can be multiplied by any kind of fields here. It doesn't matter. Just it depends on lambda, delta, not lambda, sorry. That. And also this psi, this other partial observable, also is ultra local. And this is the case, for example, in general relativity. Then this weak equality is something that solves all the problems. Namely, on the constant hypersurface, say this term here, which is this one, involving only, of course, the first integral, and also just involving this multiplied by this one, not all the others. So selecting only the x1 terms. But I didn't write this tau here because it was too long to write. So all this one is weakly equals to this Poisson bracket, but with this merged constraint, just because this is ultralocal. And this means that now we are not more concerned to evaluate this Poisson bracket between this partial observer, just this field, and the constraint at different points, but just the point where this merged new constraint given by this, of course. So we don't have basically x1, the coordinate in here, but this holds only if this test function just at the point x1 equal x is equal to 1, namely just when we have this Dirac delta between x and x1. So since this equality at least weakly holds, we can write the complete observable in this other way. That is, we have just, okay, again, infinite Poisson brackets that we have to calculate, but at least the constraint, there is no more integrals, and all the fields here are the same, evaluated at the same x as the partial observable that I want to measure. Yeah, and this constraint here now don't depend on the points anymore. And yeah, this is the last thing that I want to say, because yeah, I thought that it was very long, and so I just cut the other parts with this, namely this is a complete observable between psi and all the other t evaluated at the same point. And we can also, as you can see, compute the derivative of this f with respect to tau, and we get a dynamics of this. And that's exactly what happened in general relativity. Yeah, I guess this all, the last part is a bit of a mess, I know, but I didn't know how to simplify this structure. Do you have some question?
Yeah, so I'll start with one short question. So I just noticed at the very beginning, you said that this formalism is not very popular, or that not many people use it. So
Yeah.
is it because it's not well known, or is there some problems, or?
No, there actually, yeah, there are some problems, but because this is very important, for example, in general relativity, it's being used in general relativity to get a time, that is to get a complete observable, which can be expressed as just a combination of other partial observable, for example, where the dynamics is a good dynamics, namely just the time derivative with respect to some, say, time of that complete observable gives a well-defined dynamics. Otherwise, we don't have a well-defined dynamics in general relativity. I mean, at least quantum gravity, just in quantum gravity sector, for example. But this led to some problems, namely that so far we don't know any specific complete observable for general relativity. Namely, if we don't fix, for example, the background, if we don't add some symmetry, like, say, for example, the space-time has to be asymptotically flat, or, for example, we have a de Sitter space or anti-de Sitter space. If we don't have these extra symmetries, we don't fully know any of this complete observable. That's why it's not simple. We know, for example, in the ADM formalism, where we treat the space-time as asymptotically flat, for example, 10 charges, which are, say, conserved over time. Also in the de Sitter and the de Sitter space, we know some specific complete observable, but for general arbitrary manifold M, we don't know. That's why it's very hard. But nowadays, some perturbation theory in this exact formulation has been implemented, and it's getting some good results. I don't know yet because it's far beyond, but I think this is why it was not very used, but it's specific for general relativity. That's why you can basically explain almost everything from the theories that we already know.
Okay. Thanks.
Some other questions?
Maybe I can ask one thing again if I just wanted to make sure that I understood correctly the example with the 1D harmonic oscillator. So you have these two solutions. So it's classically, you can just solve for Q and P, which depend on time, and
Yes.
or you can have like the orbits in phase space, which is this ellipse. But if you want to have something that is gauge independent, so it doesn't, let's say, depend on time, right?
Yes.
So if you have Q and P, they both depend on time. And so the purpose of this F function would be to make a relation between Q and P, which are both functions of T, and eliminate this T.
Yes,
So
exactly.
you get something which
Yeah,
doesn't depend.
Yeah, exactly. You can get this. I mean, for example, in this case, you can just invert T and get Q, namely T expressed as a function of Q, and just substitute here, and we get the same thing that we got at the end.
Yeah.
So in this case, it's very simple, but of course, for more complicated system, it doesn't work like this. And of course, I want also to stress the fact that this is just these are just two simple functions, but we can get any function, partial function, because the space of the smooth function is infinite. So we can get infinite kinds of partial observable. But the most important thing is that they had to have at least a physical meaning. So for example, we can also take the Hamiltonian itself as a partial observable. But then, of course, nothing changes because, the Hamiltonian is conserved. So the Poisson bracket between the Hamiltonian and the Hamiltonian itself is 0. Also, we can calculate, for example, the kinetic energy or the potential, doesn't matter. And we would have for example, the kinetic energy with respect to Q or with respect to P. So we can have infinitely many possibilities, but it depends only on how you relate them. And this is exactly the way that we do. This is, for any C, any kind of C, just independent of the gauge we have.
And is there some rule to the number of partial observables? Is it that if you have some set of partial observables, as you said, then you will always get one complete, or?
Sorry, no,
maybe...
I didn't. Sorry, I didn't hear. Can you repeat?
So do you always get one complete observable, let's say for two partial, or if you add more partial observables, can you get more complete observables?
Well, I said that we can get basically one or more than yeah, one or more functions, but they express the same partial observable. So of course we won't end up with two different functions. It's just the same function, but it can be multivalued.
Well, I meant more if, so you here you have like two partial observables T and F. So if you add some more partial observables, like you said, the kinetic energy and potential energy or something, if you had more complicated system,
Yeah.
And you would construct the set of complete observables F with each of the pairs, would you get like different complete observables, or would it be the same?
Yeah, of course. Yeah, of course. I mean, we can choose whatever we want. It depends on what we are looking for. That's why in general relativity is not so simple, because yeah, at least in classical mechanics, we know just the position, for example, the momentum, the kinetic energy, the angular momentum, the spin, and so on. So we already know the meaning of that. But in general relativity, for we don't know basically what kind of observable to look for. So yeah, of course, it depends on the pair that you choose in the beginning.
Yeah, okay, yeah, thanks.
Okay, if there is no some other question.
Yes, so do we have some more questions? Yeah, okay, so maybe if not, then thank you.